Hello and welcome to this module on logistic regression. So, we looked at the problem of classification earlier, and here is an example from one of the earlier modules. So, the users marked in brown here are those who bought a computer, and those marked in red are people who did not buy a computer. And the goal of classification, we said earlier, is to find a decision surface that will help us separate people who buy computers from those who did not buy computers. There are different ways in which you could have these decision surfaces, and we looked at a few. Well, let us step back and ask the question, what exactly does this decision surface mean? Specifically, let me ask the question, what does a data point that lie on a decision surface belong to? Is it buy computers or does not buy computers? So, one way of thinking about it is to say that this decision surface denotes all the data points for which the probability of it being red is equal to the probability of it being brown. This essentially means that for the points on the boundary, the decision boundary, you are not able to make a decision as to whether he will buy a computer or does not buy a computer. Right. So, what does it tell us about the points that lie to one side of the boundary? So, the points that lie to one side of the boundary are those where the probability that the person will not buy a computer in this case is higher than the probability that he will buy a computer. So, the one way of thinking about the decision boundary is that it models all the points where both the classes are equally likely or equally probable to occur. Right. So, if you want to go beyond classification, so you might be interested in knowing what is the actual probability of a specific class given a data point, not just in finding the right classification. You would really like to know what is the probability that the person buys a computer given the age and income of the person versus the probability that the person will not buy a computer given the age and income of the person. So, why would you want to know this kind of probability of the class label? Right? So, one example is you could think of in the medical domain. Suppose I say that you have a specific disease, right, or the patient walks into the hospital and the doctor says that the patient has a specific disease, right, and you would like to know if how confident is the doctor of the prediction, right. So, if the doctor says I am 95% sure that this patient has the disease, then you certainly would go into the treatment, right. So, likewise, when you have a classifier that is going to give you a class label, you would like to know how sure the classifier is of the class label, and that is one application where you would like to see these kinds of probabilities. Right. So, one way to approach predicting probabilities instead of just the class labels could be to treat it as a regression problem. So, let us stop and think about how you would treat classification as a regression problem. Right. So, normally in classification, right, so you have labels, right, does not buy a computer or buys a computer. So, instead of using these as labels, you could use an indicator variable for the class. Right. So, if the user is or the customer is going to buy a computer, I would say the output is 1. If the customer is not going to buy a computer, I would say the output is 0. Right. Now, your data gets transformed into a regression problem now instead of a classification problem, where you have zeros and ones as your response variables and the actual attributes of the data as the predictor variables for the regression problem, right. And you could use linear regression here. We all know about linear regression now. You could use linear regression here, and finally, the function that you fit f of x can be interpreted as the probability that the output y will be 1 given the data x. Right. That seems like a reasonable way of doing classification, right. So, whenever the probability is greater than 0.5, you would say that x belongs to class 1, the probability is less than 0.5, you will say x belongs to class 0. Right. That's actually a valid way of doing classification using linear regression, but there are some problems with that. So, what are the problems? So, linear regression is not really limited in range, right. Linear the output can go from minus infinity to plus infinity. So, typically this output cannot be interpreted as a probability. Very troublesome is the fact that the output can be negative, and therefore, it certainly cannot be interpreted as a probability. even if you think of doing some kind of normalization. Right. Having said that, I should say it actually works in practice. Right. If you do not really want to treat it as probability, but just as a classifier, if it is greater than 0.5 take it as 1 and lesser than 0.5 take it as 0, it works well. It works in practice, but not that well. I mean, there are ways of doing better than just using simple linear regression. Right. So, I want to use linear regression still, right, but I am going to do that on a transformed function. Right. The transformation that we are going to talk about here is called the logistic function or the logit function. Right. So, let us have some notation here. So, let p of x denote the probability that the output y is 1 given x. Right. Then the logit transformation is given by the logarithm of p of x divided by 1 minus p of x. So, if you think about a binary problem, so p of x is the probability of it being 1, right, probability of the output being 1, and 1 minus p of x is the probability of the output being 0. So, essentially you are taking this ratio of the probability of success to the probability of failure. So, this is known as the odds, right, and so this is sometimes known as the log odds function. Right. So, now what are we going to do in logistic regression is essentially try to fit a linear regression model to this logistic function as the output. Right. So, essentially we end up saying that your log of p of x by 1 minus p of x can be modeled as some linear function which is beta naught plus x times some beta 1. Right. So, if you think about it, you can solve for p of x from this kind of an expression, right, and then you end up having p of x looking like a sigmoid function. Right. So, e power beta naught plus x beta divided by 1 plus e power beta naught x beta, and you can simplify that, and the functional form that you are going to get is something like this. Right. So, you can see that it behaves like a probability function. So, it runs only from 0 to 1, right, and by varying the value of beta, what you are going to do is you are going to vary the slope, right, and by varying the value of beta naught, you are going to vary where the function is going to rise. Right. So, this gives us a very valid way of fitting probabilities. There is no problem with interpreting p of x fitted in this fashion as a probability. Right. So, earlier trying to interpret f of x in a linear regression model as a probability had problems. Right. So, we could not do that because it could be negative as we saw earlier, but in this case, since p of x is going to be limited between 0 and 1, we might as well interpret it as a probability. Is it the right model for doing it? That is an open question. It depends on the domain that you are working in, but it is fairly widely used, and it is very powerful. It results in a very powerful classifier, and which you can use in a variety of different settings. Whether this assumption is actually supported by the data or not, it seems to work well in practice. Right. So, as we did with the linear regression case, we will predict the class is 1 and the probability of x is greater than 0.5 and 0 otherwise. And this essentially we can show if this minimizes the misclassification rate given the form of the predictor that we had on the previous slide. Right. One thing to note, so even though p of x is given by this exponential function, right, the actual classification boundary, right. So, what is the decision boundary? Decision boundary is the point where the probability of class 1 is equal to the probability of class 2, right, or class 1 and class 0 probabilities are equal. So, with a little bit of thought, you can see that the decision boundary is still given by a line which essentially beta naught plus x beta 1 equal to 0, right. So, that gives you the decision boundary of the logistic regression classifier as well, and hence this is also a linear classifier. Right. And I mentioned earlier, it is pretty powerful and works well in practice. So, let us look at an example of what happens when we fit data using logistic regression versus linear regression. So, here is a 2 class problem. So, the data points are either in blue or in red, and the shading in the region indicates what is the class label that would be predicted by the classifier in those regions. Right. So, on the right hand side you have slides, you have the prediction made by fitting a linear regression to the indicator variable. On the left hand side, you have the output given by logistic regression. So, you can see that a linear regression actually makes certain errors closer to the boundary, right. That is because linear regression is essentially limited at the rate at which the curves can climb, right. And when closer to the boundary, when there are points that are bunched together from one class and a little farther away from the rest of the class, linear regression is not able to model those successfully. While logistic regression, by virtue of the fact that you could have a steep climb from 0 to 1, is able to capture those data points. So, this is essentially the difference between linear and logistic regression. So far, I have been talking about binary classification problems because they are easier to illustrate and kind of understand the basics behind. But then logistic regression can be extended to the multiple classes as well. Suppose there are k classes, then I would say that each class gets a different set of parameters beta naught and beta for that specific class. Okay. So, in that case what happens is your probability of so the probability that a particular class is the right class for a data point is given by e power beta naught of c, which is the e power beta naught of c plus x beta c, which are essentially the parameters specific to that class, and divided by the total the normalizing factor, which is essentially the numerator summed for all the data points, right. To make the problem somewhat easier, traditionally the parameters of one of the classes, it could be either the first class by numbering from 0 to k, or it could be the last class, which is k, right, is set to 0, and you can think about it, it really does not affect what the the decision boundary that you are going to learn. Okay. It will change the parameters that you are learning, but the decision boundary that you learn will not be affected, right. So, in a sense you will be left with fewer parameters that you have to estimate. That is because we are talking about probability distributions here, and we know that as soon as you fix n outcomes in a discrete probability distribution, then the the probability of the n plus 1th outcome is automatically fixed, right, in total of n plus 1 outcomes, right. So far we have been looking at the basic model logistic regression, and I will end this module here, and from the next module we will look at how we will actually learn the parameters of this logistic regression classifier.